Good day, everyone. So today I will discuss about empirical and molecular formulas. Okay, so there are three main types of chemical formulas: empirical, molecular, and structural formulas. So empirical formulas shows the simplest whole number ratio of atoms in a compound, while molecular formulas show the number of each type of atom in a molecule. And structural formulas show how the atoms in a molecule are bonded to each other. Okay, so how can we represent a molecule? So the most obvious way is its name. So for example, you could be referring to a molecule benzene, but just the word benzene tells you very little about what actually makes up this molecule. But you may say, well, I actually want to know more about the actual particular elements that make it up. Well, in that case, it might be useful to move up to the empirical formulas. And you might be thinking, what does empirical mean? In general, the word empirical is referring to something that achieved through observation or comes through experiment. The early chemists, they can't look. They weren't able to look at just one molecule, but uh they could at least come up with they could observe the ratios of the different elements that they had in a molecule. So an empirical formula gives you a ratio of the elements in the molecules. So an empirical formula for benzene, one carbon for every one hydrogen. Now, you might say, well, okay, that's nice. I know now that if I'm dealing with benzene, I have one carbon for every one hydrogen. But what does or how many of each of these do you actually have in a benzene molecule? To answer that question, that's when you would want to go to the molecular formula. Okay? And the molecular formula for benzene, which is now going to give us more information than the empirical formula, it tells us that each benzene molecule has six hydrogens and six carbons. Now, the ratio is still 1:1, right? You get that right over here. Okay, so you have six carbon and then six hydrogen. So it's very easy to go from molecular formula to empirical formula. Okay, so it's a ratio of 6:6, which is the same thing as 1:1. That may not satisfy you, and you might say, well, okay, but how are these carbons and six hydrogens actually structured? And for that, you would want to go to a structural formulas, which will actually give you the structure or start to give you the structure of a benzene molecule. And a benzene molecule would be drawn like this. All right. So you would have six carbons in a hexagon. So you have one, and then going to have this way, two, three, four, five, and then six. So you have six carbons in a hexagon just like that. And then you have a double bond. Every other of these bonds on the hexagon is a double bond. So each of these carbons are also attached to a hydrogen, also bonded to a hydrogen. So each of these lines is a bond. Okay, these are bonds. Okay, so it's actually a covalent bond. And that's what keeps this carbon near each other and what keeps the hydrogen kind of tied to each other or the the hydrogens tied to the carbons and the carbons tied to the hydrogens. All right. So this is just one variant of structural formulas. Okay, so there's multiple ways to do a structural formula, and we will talk about it next meeting on our next topic, which is the structural formulas. All right. Now, I want to make clear that empirical formulas and molecular formulas aren't always different if the ratios are equal. Also, show the actual number of each of those elements that you have in a molecule. So a good example of that would be the formaldehyde, okay? And also water. So water, we all know for every two hydrogens, you have an oxygen. So a molecule of water has exactly two hydrogens and one oxygen. All right. So each of those oxygens in a water molecule are bonded to two hydrogens. So we're done talking about chemical bonding. So I think you know what I'm talking about this hydrogen and oxygen bonding. Anyway, so while the ascorbic acid have different ratios for its empirical formula and molecular formula, they are quite different. All right. Well, there are also compounds that have exactly the same empirical formula, but very different composition and name, of course, just like ethene and cyclopropane. They both have an empirical formula of CH2, but these two substances are very different products, okay? And they have different molecular formula, different name, different composition, different properties, but they have the same empirical formula. All right, so you have to take note of this. Ionic compounds are always empirical because these are ions, okay? They are not molecules, so they are ionic compounds, just like uh, barium chloride, okay? Magnesium phosphate. So this is the barium chloride, this is the magnesium phosphate, and then we have the sodium chloride, and then the calcium chromate, okay? Now, for empirical formula, we can use percent composition data to determine the compound's empirical formula, which is the simplest whole number ratio of elements in a compound. Okay, so there are steps to follow in calculating the empirical formulas. Step 1, calculate the number of moles of each atoms by dividing the amount, which is in terms of grams, by its atomic mass. So if the given is in terms of percentage, you must have a basis of 100 grams. Next step, convert the results to whole number ratios by dividing each number of moles by the smallest number of moles. And step 3, this is only if necessary or this is optional, you have to multiply each number by an integer to obtain whole numbers. All right? So let's have an example. So our first example, calculate the empirical formula of a compound composed of 43.64% phosphorus and 56.36% oxygen. Okay, so I'm going to assume a mass for this compound. So let's just say it is 100 grams. All right. I could have assumed 1000 grams or 5 grams, but 100 grams will make the math easy because our whole goal is to say, well, what's ratio between the number of moles we have of phosphorus and the number of moles we have of oxygen. And that will inform the likely empirical formula. Okay? Anyhow, if we assume 100 grams, well, then we are dealing with a situation that our phosphorus, we have 43.64 grams of phosphorus. All right? So you just have to change this percentage into grams. So it is much easier since you only have a basis of 100 grams. All right? Okay, so we can figure out how many moles this is by looking at the average atomic mass of phosphorus. That's why the periodic table of elements is useful. So you can just check your periodic table, and you can see that the atomic mass of phosphorus is 30.97 grams per mole. All right. So grams per mole is the unit of the atomic mass of phosphorus. However, in this case, we have to bring down, okay, or to put or to place the grams at the denominator and then the mole at the numerator so we can cancel out these grams. Okay, so we can cancel out these grams. Okay, so now we could multiply this times 1 over 30.97 moles per gram. So when we multiply this out, the grams will cancel out. Okay, and we're just going to be left with a certain number of moles. So using your calculator, you can use your cell phone calculator. I'll take 43.64 and we're just going to divide it by 30.97. All right, it is going to be equal to 1.409 mole of phosphorus. Okay, now I can do the same with oxygen. Okay, so oxygen, if I have 56.36% by mass, so 56.36% of 100, which I'm assuming is 56.36 grams of oxygen. So, and how many grams per mole? So, if I have 1 mole of oxygen on average on Earth, the average atomic mass is 16 grams per mole. Okay, so you can check this out in your periodic table. That the atomic mass of oxygen is 16 grams per mole. And so this is going to approximate how many moles because the grams are going to cancel out. All right, so once again, you can cancel out these grams. Okay, so cancel out these grams. And we take 56.36 grams of oxygen divided by 16.00 grams. It gets us to 3.523 mole of oxygen. Okay, and remember, we are talking about moles, and this is how moles of phosphorus we have, and this is how moles or how many moles of oxygen we have. All right. Okay, so the next step is divide each moles by the smallest number of moles, which is 1.409. Okay, and then we'll get a ratio of 1 for phosphorus and 2.5 for oxygen. Since we did not get a whole number ratio for oxygen, all right, so this is the ratio. It's actually 1 for phosphorus is to 2.5 oxygen. And since we did not get a whole number ratio for oxygen, we then find a number or an integer that would make it a whole number. So let's multiply this by 2. All right. And we have an empirical formula P2O5, or the name is diphosphorus pentoxide. All right? So this is your empirical formula. Okay, so let's have another example. Analysis of a certain compound show that it contains 0.883 grams of hydrogen, 10.497 grams of carbon, and 27.968 grams of oxygen. So you have to calculate the empirical formula of the compound. So we will skip the conversion from percentage to grams, since what we have here, the given is in terms of grams already. So the next step is you have to convert the mass to moles. Okay? So for hydrogen, we have the given 0.883 grams of hydrogen, and then multiply it by its atomic mass. Okay, it's from your periodic table. So 0.883 grams divided by 1.01, it would give you 0.874 mole of hydrogen. Okay, and then we can cancel this out, the grams. Okay, and then the next is we have carbon. So the given is 10.497 grams of carbon divided by the atomic mass of carbon, which is 12.01 grams per mole. So once again, you can cancel out the grams, okay? And then we will come up with 0.874 mole of carbon. The next step is finding, or the next is you have to find the mole of oxygen. So we have the given 27.968 grams of oxygen divided by the atomic mass 16. And it would give us 1.748 mole of oxygen. All right. So this is also canceled. So it would leaves us with the unit of mole. Now take note of the smallest mole, number of moles, and that is 0.874. So we will use that for our next step, where you have to divide the moles, each moles of the atom by the smallest number of moles. So for hydrogen, divided by 0.874, so we have a ratio of 1 hydrogen, and then we have 1 carbon, and then we have 2 oxygen. So it would give us a ratio of 1 carbon is to 1 hydrogen is to 2 oxygen. So the formula is CHO2. So the step 3 is not necessary since we already have the whole number ratio. So this is your empirical formula. All right? Let's have another example. Okay, calculate the empirical formula of a compound composed of 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. So since the given are in terms of percentage, we will have a basis of 100 grams. Okay, so this percentage, you just have to change this into grams, okay, into the unit grams. So let's convert all the mass to moles. So we have 38.67 grams of carbon divided by its atomic mass. So that is 12.01 grams per mole. So cancel out the grams, and it would leave us with 3.220 mole of carbon. Okay, and then the next one, we have the hydrogen. We have 16.22 hydrogen divided by 1.01 grams, which is its atomic number, or rather atomic mass. And then you have to cancel out the unit grams. So it would give us 16.06 mole of hydrogen. Okay, and then the next one, for nitrogen, we have the given 45.11 grams of nitrogen divided by its atomic mass, which is 14.01 grams. So cancel out the grams, and it would give us 3.220 mole of nitrogen. So take note the smallest number of moles, which is 3.220, which we will use in our next step. Okay, so the next step is you have to divide by the smallest number of moles. So we have the ratio for carbon is 1, and then the ratio for hydrogen is 1, or rather 5, and then for nitrogen, it's 1. So our ratio is 1 carbon is to 5 hydrogen is to 1 nitrogen. So in this case, we don't have to go on to the third step since we already have a whole number ratio. Okay, so therefore our empirical formula is CH5N. All right, so this is already your empirical formula. Okay, so now let's move on to how to find the molecular formula given the molar mass of the compound. Okay, so try to analyze this set of empirical formulas. Okay, so we have the empirical formula CH2 with the empirical formula mass of 14.03 grams per mole. And we have those molecular formula C2H4, which has an equivalent molecular formula mass of 28.06. And then we have molecular formula of C3H6 with the molecular formula mass of 42.09. And then we have C4H8 with the molecular formula mass of 56.12. So what pattern can you see from this set of molecular formulas as well as the empirical formula? All right, so the molecular formula is a whole number multiple of the empirical formula. All right, and not only the formula, but also the mass. Okay, so that's the pattern you can see in this given molecular formula and empirical formula. Okay, so once again, we have steps to follow in the calculating the molecular formulas. Step 1, determine the mass of the empirical formula. So for some problems, you may have to calculate the empirical formula first. All right. And then step 2, you have to use this formula to get the factor. So factor or F is equal to molecular formula mass over the empirical formula mass. And then step 3, you have to multiply the F factor by the subscript of the empirical formula. And that would be equivalent to your molecular formula. Okay, so let's have some examples so you would understand more on how to calculate the molecular formulas. Okay, so we have the empirical formula. Okay, so the empirical formula of a compound is C2H4O. The molar mass is 132.16 grams per mole. What is the molecular formula? Okay, so we have the given empirical formula, which is C2H4O, and we have to find the molecular formula. So the first thing we need to do is to find the empirical formula. All right, so there are two, so we have the empirical formula of the compound. We have 2 carbon, all right? and then we have 4 hydrogens and 1 oxygen. So let us first find the empirical formula mass. Okay, so we just have to use all those number of atoms. So there. So you have 2 atoms of carbon, okay, multiplied by its atomic mass, where you can find it in your periodic table. And then you have 4 atoms of hydrogen, multiplied by its atomic mass, 1.01. And then you have 1 atom of oxygen, and then multiply it by its atomic mass. All right? So just add up, and you will get 44.06 grams per mole as your empirical formula mass. Okay, so now we need to know what empirical formula, or rather what molecular formula corresponds to a molar mass. Okay, 132.16 grams per mole. So what you need to do is to take the larger number, okay, to take the larger number and divide by the small number. So we have this formula for a factor, molecular formula mass over the empirical formula mass. So the molecular formula mass is also the same as the molar mass, is 132.16. And then the empirical formula mass is 44.06. So let us substitute. So we will get a factor of 3. Okay, so we get the factor of 3. So therefore, to get the molecular formula, we need to multiply the subscripts of the empirical formula by 3. So this is going to give us, okay, C6H12O3. All right? So that's how you find the molecular formula from the empirical formula. Okay? Now let's have another problem. So determine the molecular formula for a compound that is 50.7% carbon, 4.2% hydrogen, and 45.1% oxygen. The molar mass for the compound is 142.00 grams per mole. Now take note of this. You cannot find the molecular formula if the problem has no given molar mass. Okay, so it is necessary that the given problem have the molar mass of the compound so you can find the molecular formula of the compound. Okay, so so in this example, we were given a percent composition, okay, which we convert it into grams. So anyway, here we're given the grams of all the elements in this compound. So we're going to follow the same steps of converting each into moles, all right, from the given atomic mass in your periodic table or from your periodic table. Okay, so we have 50.76 grams of carbon, and then divided by 12.01 grams. So that's 4.22 moles of carbon. So now let's turn our attention to hydrogen. So the atomic number, rather atomic mass is 1.01 grams of hydrogen per 1 mole. And so this is going to be 4.2 mole of hydrogen. And finally, let's move to oxygen. We have 45.1 grams of oxygen, and the atomic mass is 16. So this will give us 2.82 moles of oxygen. So you have to cancel out all these grams, okay? So that your answer would be in terms of moles. Okay, so your answer is in terms of moles. So now let's divide each number by the smallest of these three values. So the smallest is 2.82 mole. So 4.22 divided by 2.82 is equal to 1.5 carbon. Okay, so this is the ratio of carbon. Then 4.16 divided by 2.82, we have 1.5 hydrogen. And okay, so next is for oxygen. So this is obviously 1. So let's find a multiplier. Since looking at this, we have the ratio 1.5 carbon is 1.5 hydrogen is to 1 oxygen. So we don't have a whole number ratio for this formula. So therefore, we have to find a multiplier to make it a whole number ratio. And an empirical formula, there should be, okay, there should be 3 carbon atoms, okay, 3 hydrogen atoms, and 2 oxygen atoms. So the formula is going to be C3H3O2. So this is the empirical formula, okay? So let's move on to the next step. Now let's find the molecular formula. So to do that, we got to find the empirical formula mass. So we have 3 carbon atoms multiplied by its atomic mass. And then we have 3 hydrogen atoms multiplied by its atomic mass. And then we have 2 oxygen atoms multiplied by its atomic mass, which is 16. Now let's add up the numbers that we see here. So this adds up to 71.06 grams per mole. So that's the molar mass of the empirical formula. Okay, and we also call that as empirical formula mass. Now we need to find out the molecular formula that corresponds to 142. So what you want to do at this point is to take, okay, the molar mass of the molecular formula and divide it by the empirical formula mass to get the factor. So that would be 142 divided by 71.06 equal to 2. So therefore, we need to multiply the subscripts of the empirical formula by 2. Okay, so you have to multiply 2 by 3 for carbon, and then 2 times 3 for hydrogen, and then 2 times 2 for oxygen. All right. So the formula is C6H6O2. So that's the molecular formula. Okay. Now, you know how to find the empirical formula and the molecular formula if you're given the percent composition by mass or if you're given the grams of the elements in the compound. All right. So this is how you calculate the molecular formulas. And this is quite necessary or important when we deal with structural formulas. Okay, so for the challenge problem, what is the molecular formula of a compound composed of 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and 16.5% oxygen? The molar mass is about 195 grams per mole. All right? So again, first two students who can send me the correct answer will be exempted on our next quiz. And then the succeeding three students who would send me the correct answer will get plus 10 points on the next quiz. All right? So that's all for today. Thank you and God bless.